got chapter 3. This is the last section of chapter 3, 3.3. The other two sections we did as part of our unit on atomic history. So the first slide. You gotta be kidding me. It is. There we go. The first slide. This is so very basic at this point for you. 2 in the morning, it could shake you awake. You would know this. You know that there are 3 subatomic particles we talk about, and that there are generally 2 neighborhoods in the atom, as it were. There's the nucleus and everything that's not in the nucleus. So let's do a little bit of review on atomic theory and structure. So in the nucleus we have 2 subatomic particles. They are protons and neutrons. You knew that. Outside the nucleus, we used to think there were these neat little racetracks, right? What do we call those neat little racetracks? Wait, I heard 2 different words. Orbits. The neat little racetracks were orbits. Like the moon orbits the planet. Like the planets orbit the sun. Now we know, thanks to Heisenberg and Schrodinger, that we can't really pin down electrons that well. But there are these big fuzzy areas where we have a good likelihood of finding one. What do we call those big fuzzy areas? Orbitals. There we go. So we've got orbits and orbitals. And those orbitals are all outside the nucleus. That's where we find our electrons. Okay. Oh, wonderful. Okay. So, who found the proton? You remember that? Or, I'm sorry, not the proton. Never mind. We'll get to that. Okay. So protons. Well, who confirmed the existence of that little dense central nucleus? Rutherford. Okay. So we've got the dense central nucleus with the protons with a positive charge. The neutrons. Who found the neutron? Good old Jimmy. James Chadwick. And somebody said in the other class, is that where Jimmy Neutron came from? I don't know, but it's a good way to remember it. So, yeah, James Chadwick, Jimmy Neutron. So look at the masses that are on your notes of the proton and the neutron. What do you notice about them? They're pretty darn close. Yeah, the neutron's got the proton by a little tiny bit. But we're out to -10 to the -27th. So that's like a gazillionth. It's like 2 gazillionths. So they're pretty much the same mass. They're pretty close to the same mass. What we do is we level that off and we say they're even. So we say that they actually have the same mass. They don't quite, but we approximate. Okay, now, here's a weird bit. What's true about 2 things with like charges? What do? Repel or attract? They repel. So we got a whole bunch of protons living in this tiny little nucleus. This is like a bunch of siblings living in a shoe. What was the old one who lived in the shoe? Yeah. You got a bunch of people in this tiny little space. You have a bunch of positive protons in this tiny little space. Why aren't they all kicking one another out? Well, the neutrons don't exactly cancel them out, but the presence of the neutrons does have an effect. There is something called nuclear force. And actually, nuclear force is one of the 4 fundamental forces in the whole universe as we know it. There's strong and weak nuclear force. We won't talk about them a whole lot more than to say that they exist, but that's what allows all those protons to stay in that nucleus and not push one another out of the nucleus. It's what holds nucleuses together. Now, we measure atoms in picometers. You know your prefixes very well for the metric system, for the SI system. Some of you are giving me hairy eyeballed looks like I don't know it very well. But picometer is what power of 10 of a meter? -12. So 1 times 10 to the -12 meters is a picometer. That's pretty darn small. And a nucleus is actually 1,000th of a picometer, roughly. So these things are tiny, tiny, tiny. They are indivisible. So Democritus thought, but more than that, they are invisible. Now, interestingly enough, a few years ago, the first image of an atom was obtained. It was an image of a single atom. This was, I want to say 5 years ago, and I want to say someplace like Caltech. And it was published find it online. I should have a picture in here of it. What you see is a fuzzy orb. Fuzzy ball. That's all you can see. But it was, and it's not like a real light image. It's probably, I don't know if it's a diffraction image or what. But you can see an individual atom, which is pretty amazing because that's pretty darn tiny. Moving right along. So we're going to talk now a little bit about atomic mass. And if you would be so kind as to get out your books. If you don't have a book, you can use your agenda. And look at the periodic table, which is either on the back flap of your PEM textbook, or if you have a rebind and there's no periodic table there, there's one on page 131 or 113. One of those two, 131, 113. Which is it? 130, 131. Okay. Good. So we're going to talk about atomic mass, and I'm going to move this up to the board.